Well, good morning, everybody. It's my great pleasure to introduce today's plenary speaker, Professor Kerry Vahala from the California Institute of Technology. Kerry is the Jenkins Professor of Information Science and Technology and a professor in the Applied Physics Department at CalTech. He also received his bachelor's and PhD from CalTech, so he is CalTech to the core. Kerry pioneered the study of nonlinear optics in high-Q optical micro-resonators. And in the course of this work, his research group demonstrated the highest quality factors for an optical micro-resonator on a silicon chip. They have used these devices to study a wide range of nonlinear phenomena, including parametric oscillation, Brillouin scattering, Raman processes, and cavity optomechanical gain and cooling. The devices are also being applied to the study of gyroscopes and Soliton microcombs. Kerry was also involved in the early effort to develop quantum well lasers for optical communication systems and received the IEEE Sarnoff Medal for his research in this area. He has also received an Alexander von Humboldt Award for his work on high-Q optical microcavities, a NASA Achievement Award for application of frequency combs to exoplanet detection, and is a fellow of the IEEE, the IEEE Photonics Society, and the Optical Society of America. He's a frequent traveling lecturer for the Optical Society of America and has published over 200 refereed journal articles and has over 30 patents in photonics. And just as a personal note, Kerry and I shared the same thesis advisor, and I arrived at CalTech a few years after Kerry had finished his thesis work. And really the work that he did as a graduate student in CalTech really provided a foundation for basically everything that I did. And within the first 6 months of arriving there, I had read all of Kerry's papers, and they very much benefited me in terms of my future research. So please welcome Kerry Vahala.
Thank you, John, and also I want to thank the organizers for the opportunity to be here and tell you about this recent progress towards the integration of optical time standards and frequency synthesizers. And it's an area that's heating up very nicely right now. There was a great talk yesterday given on one of on the time standard project team that we're involved with. What I want to do first, though, is because the background of the audience is quite broad, I wanted to define what we're talking about today in terms of the optical frequency synthesizer and the optical clock. I know many of you are experts in this area, but I thought it'd be a good starting point anyway. So the synthesizer, the optical synthesizer, is going to take a radio frequency reference. So here I'm showing oven-controlled quartz, and it's going to convert that stability, transfer that stability out to the optical domain, and then synthesize on-demand frequencies with that corresponding stability. That will be its job. The clock goes in reverse. So the clock is going to begin with probably an atomic time standard, although if we wanted to not use this as a clock but as an oscillator, we could use something with less stability, perhaps a microcavity or a very stable cavity or a stabilized laser, transfer that stability down to the electrical domain, and then process it for some purpose. And of course, the device that does this is an optical frequency comb, which has now been studied for nearly 2 decades. And what makes it, I think, very, very powerful is that what it allows us to do is to actually leverage and share the respective advantages of all the work that's happened in radio frequency and microwave with all of the work that is also ongoing in optical research and optical communications. And so, for example, radio and microwave components that would be on the left side of the chart, they provide all of the very beautiful advanced frequency reference technologies like oven-controlled quartz, masers, and so forth. There's also obviously extremely sophisticated circuits for processing, for control, and also for human interface, something that really doesn't exist yet in optics, probably never will. On the other hand, optical components now are entering their 4th decade of development for fiber communications, and so they're also extremely sophisticated now. And in the context of synthesizers and clocks, obviously what optics brings to the table is extremely high frequencies in the hundreds of terahertz, but with very, very low loss. And so we have tremendously high Q factors in those systems, which are important, obviously, at the center of a lot of the clock technology. So this is what we mean. We have this sort of bidirectional, coherent link now between these two worlds, and I'll be focusing, obviously, on this link, but it's miniaturization and how that's enabling these new integrated technologies. And so here's what the kind of roadmap for today. I want to begin, again, just to make certain we're at the same starting point, and because our backgrounds are so diverse, very quick review of frequency comb technology, which is laying the groundwork for everything that's going on now with microcombs, these little miniature frequency combs. The second part is the main part of the discussion today, and I'll be looking at these microcombs, the platform that we use, the physics, and also how they're now being engineered to realize actual self-reference comb systems. And then the final part, I'll dive into some of these recent chip-based demonstrations that are ongoing. I'll spend most of my time talking about the synthesizer because there was a great talk given yesterday by one of our team members on the clock. And so I really only have one chart on the clock, and then summarize. So combs, all right? So again, many of you know a great deal about combs, but let's talk about it anyway. So at the heart of every frequency comb, there's a mode lock laser, and so this is meant to be a little animation provided to me by Scott Diddams at NIST, showing a TISAF mode lock laser. So there's 4 mirrors. You see these pulses running around between the 4 mirrors. One of the mirrors is partially reflecting, and so the pulses are coupling out and providing this periodic femtosecond pulse stream. If you were to spectrally analyze, say, in a grating spectrometer, the pulses that are emitted, you might see a spectrum like what I've painted in over there in the optical domain, and it would have some bandwidth that would be inversely proportional to the pulse width. If we had a little bit higher resolution and took out a little narrow slice of that spectrum and looked at it more closely, it would be possible to actually resolve the frequencies of the comb, the actual comb lines corresponding to the modes, the longitudinal modes of that mode-locked laser. And here you can see the repetition rate, f-rep, which is 1 over the round trip time of the cavity. And I've also labeled one of the comb frequencies, f sub n. And so central to the idea of frequency combs is that we're going to describe those individual frequencies of that comb in terms of 3 parameters. One is just an index, an integer index on the frequency. The other is the repetition rate. And then the third parameter is extremely important, and this is central to the idea of frequency combs, self-reference frequency combs, is this FCEO, the carrier envelope offset frequency. And the idea of the FCEO is described in the kind of lower side of this plot. And turn this on in a second here. And so there's a break, okay, in the frequency scale, and then as we go down to very, very low frequencies, now to a part of the spectrum where the optical energy is no longer even present, we could still continue to paint in lines extending the comb all the way down to near 0. There would be an n equals 0 line, and the offset of that from 0 is FCEO. And so that's naturally going to be less than the repetition rate. But that's the expression that we want to keep in mind for comb. And the key idea is to measure that parameter, which is this kind of funny parameter, and it's kind of curious question of how you measure it. And this led to the whole idea and the demonstration of self-referencing. And self-referencing involves several steps. And so we begin again with the mode lock laser. You broaden the spectrum dramatically, typically using a piece of nonlinear optical fiber. So now the spectrum extends over a full octave. So factor of 2 from the low frequency side to the high frequency side, and then a couple of other steps. And so the first step, filter out a few of the lines at the low frequency end of the comb. So this gives us this set f sub n. Filter out a corresponding set about a factor of 2 in frequency away at the other end of the comb, f sub 2n. And then to make the measurement, 2 additional steps of FCEO. Double the frequencies on the low end to create these replica frequencies now that are very close in value to the comb lines at the other end of the spectrum. So this is the set 2f sub n. And now the key idea is to compare that set with the actual lines at that end of the spectrum. And so this is easy to do. It just simply involves heterodyning those lines together. So you superimpose them on a detector. This generates a photocurrent. And in one line of algebra, it's possible to show that actually FCEO emerges. And so if you measure it, you can then servo control the cavity to actually lock down in radio frequency control or impart radio frequency stability to that offset frequency. So of course, this idea and all of the ramifications of it were the basis for half the Nobel Prize in Physics in 2005, shared by Jan Hall and Ted Hench. And I think one of the incredible things about frequency combs is that there are two modes of operation, and each of those modes provide very different application spaces. And that's, I think, why they're so useful and so important in optics and spectroscopy and timekeeping oscillators, the list goes on. So the first mode kind of completes this train of thought that I started in performing the self-referencing. So if we look at a line of the comb, F sub n, we've now stabilized FCEO. If one stabilizes the repetition rate, and this is trivial to do, you simply measure the actual pulses coming out of the laser. That immediately gives you the pulse rate. That can be servoed back to the cavity length. Then you've now fully locked down the comb, and means you've locked down all the lines, and this creates what's sometimes called an optical ruler, and that leads to frequency synthesis. This is really the idea of frequency synthesis. So this is the electrical to the optical direction that I mentioned earlier. But you can do something different, and this is the second mode of operation. Pick a line, so we fix n, stabilize FCEO, perform the self-referencing, but now, rather than stabilize FREP, stabilize the line itself, F sub n. So lock that to something very, very stable. It could be an atomic transition, a very long-lived atomic transition. And now the repetition rate is stable. And so this is actually now running the comb in the other direction. And so this is the optical to the electrical direction. And this has an analogy, this kind of clockwork analogy that's used a lot. And these are, again, some nice little movies I borrowed from colleagues at NIST. But the mode 1 is showing the electrical to optical. So now the radio frequency reference is driving the slow gear, and the job of the comb is to actually translate that stability up to the optical domain to synthesize frequencies. In this case, only 2 frequencies, but obviously we can synthesize many frequencies. And then when you run it in the other direction, you're going from the optical domain down to the electronic domain, and here you get clocks and very stable oscillators and the like. Okay, so that's the quick overview of combs, and so now let's dive into the core of the talk. I want to really look at these new microcombs. To begin that, I need to actually look at the platform, which are these little microcavities that we and others spend a lot of time fabricating and studying, and primarily we're interested in their nonlinear optical properties. So let's begin there. Okay, so all of the microcavities that are used, optical microcavities that are used, or micro-resonators, in comb work are of a particular type. They're called whispering gallery resonators. Whispering gallery resonators derive their name, of course, from the acoustical whispering gallery that goes back over a century to the time of Lord Rayleigh. And the geometry of propagation is exactly the same. The light in an optical whispering gallery resonator is going to orbit. So keep in mind an orbiting path. I'm showing here pictures of a lot of the different microcavities or micro-resonators that have been used to generate frequency combs. There's a whole variety of different materials that are used, different geometries. Some are on a chip, some are off chip, but they all have in common this one feature that is kind of illustrated down here of the propagation as an oval, and so I've painted in a little green oval on that device, which is called a microtoroid, and it's a silica whispering gallery device. But it's illustrating the basic feature that the light is being guided in the dielectric by quasi-total internal reflection. So the index contrast between the glass and the air is kind of letting the light run around in a circle. And all of these other devices do exactly the same thing. Okay, so the light will orbit in a little trajectory. There's a resonance condition, and so there will be a set of frequencies evenly spaced, just as there were in the Ti-Sapphire microcomb, or a Ti-Sapphire comb that I had in the previous chart. And you'll see a couple of these geometries pop up today as we go through the presentation. I'll be drawing upon a lot of different work, but they all have in common this one idea. Now the other feature of these resonators, which is much harder to realize, it's easy to fabricate a resonator that looks like a whispering gallery, and it will actually even have support modes, But what is far more difficult to do is to make the loss very low, especially to make the loss low, in other words, drive up the optical Q, and also make the structure small. And this is a device that was developed actually for for the synthesizer program, and I'm going to use it just to illustrate why we need high Q and why the small volume is important. So this is a device that has a waveguide on it. It's made of silicon nitride, but that really doesn't matter so much. And what I'm going to show here is that we'll couple laser light into this waveguide from off the chip. The laser will tune, and at some point it will encounter a resonant. There'll be a resonance between the laser frequency and the whispering gallery. And when this happens, light will begin to circulate inside the whispering gallery, and then there'll be resonant buildup. And the key point, and what drives, I think, everything that we do and a lot of what other groups do, is that there is this very simple relationship between the circulating intensity in the cavity and the coupled power. And it scales like Q over V, the optical Q factor divided by the mode volume. And so this particular device has Qs of around 200 million. Mode volume, you can see there, it's a large device. It's a 3 millimeter diameter device. That's a largish device, okay, for whispering gallery resonators. And, but a milliwatt in will convert to 10 megawatts per square centimeter of circulating intensity. And that's not pulse, that's continuous. A couple of the other structures I had on the previous chart will do even better. A milliwatt in will get you over a gigawatt, okay, per square centimeter of circulating intensity. You can generate over a kilowatt of actual circulating power, okay, not intensity. And again, all continuous. And so what this does is it allows us to access the nonlinear optics of almost all the dielectrics that are of interest at very low powers. You can actually get into the nonlinear regime, study Raman, Brillouin. The Kerr effect will be central to everything I talk about today. You can even study things that we didn't know were there, radiation pressure coupling effects, for example, which is the basis for a field called cavity optomechanics that allows us to cool mechanical degrees of freedom and also amplify mechanical motion. And, but this is the key point. And I'll add one other thing, and that is that the threshold for oscillation and also the scaling of power in the devices that we'll describe today is also dependent upon Q, but the dependence is much more dramatic. It's inverse quadratic. And so the actual operational power of the frequency microcombs scales inverse quadratically with Q. A factor of 10 improvement in Q will actually lower the power consumption by a factor of 100. And so this is why there's been so much attention paid to Q in this little microcavity area or micro-resonator area. And here's an early example. This goes back to 2004 of a nonlinear effect. There's many I could use to illustrate how you can observe optical nonlinearities. This one is selected because it underlies all of the work in microcombs. It's actually the regeneration mechanism used for the early microcombs and also the more recent microcombs that use solitons. It's parametric amplification, which leads to parametric oscillation. And this is how it works. This is the intensity dependence of the refractive index in the dielectric. In this case, silica on the left, and this mag fluoride is the resonator system I'm showing on the lower right. And what happens at kind of the level of the photons is that this is a chi-3 nonlinearity, and so I'm showing two pump photons, green pump photons, and they scatter off of one another through this nonlinearity. They produce two new photons that are in this elastic process. One is red shifted, one is blue shifted. In the cavity, this fundamental process actually leads to amplification, parametric amplification. And so if we have some pump light, which I'm showing there is that central peak in that spectrum, there's a threshold where this parametric amplification will overcome the inherent loss of the cavity, and there'll be oscillation. In this case, parametric oscillation. You'll see these signal-idler pairs that will emerge. The frequency separation of the signal-idler pair from the central line are equidistant, and that's because this process is elastic. Something else interesting happens. After the signal-idler pair are running, there's then, now in the cavity, blue, red, green photons. And so now you can have new scattering events that involve mixing, scattering these different combinations. And so there's a cascading that begins to occur. And so you see this signal prime, idler prime, and those are the result now of actually cascaded four-wave mixing. So the process starts with parametric oscillation that gets the system going, and then once all these photons are there, then you start to create new combinations and new frequencies. And this leads us now to the early microcomb, the first idea of the early microcomb. So here's a kind of animation. So suppose we have a cavity, we pump it, there's parametric oscillation, signal-idler sidebands, continue to pump. And now what happens is that a whole series of lines unfolds. And the idea that this could form the basis for what we now call a microcomb, a way of miniaturizing a full comb, goes back to a paper in 2007 by Tobias Kippenberg. And his group used a microtoroid, and actually this is data from that paper, which you can see there's a whole forest of lines that have been created with the cavity round trip rate as a result of this combination of parametric gain, parametric oscillation, cascaded forward mixing. And so at that time, this set in motion now the work that's continued through the present day. And there was a flurry of activity for around 5 or 6 years, simply trying to use these combs and study them in many different systems. So just showing some of that work across nitride, the crystalline systems, silica, many different platforms actually realized these early kind of cascaded forward mixing combs. And just to kind of show you what happens, this is representative of what's observed. These are some silica devices that we've studied. And here, showing pumping of a cavity with just a little bit of power, about 2 milliwatts of power. And you can see essentially the pump, the signal idler, and a little bit of cascaded forward mixing. A little bit more power, 7.5 milliwatts. There's now a number of lines. Pump it even harder, 200 milliwatts, and now there's a whole forest of lines, thousands of lines, and all originating from this original pump, which you can see right here. So this actually is a very quick way, assuming that you can fabricate a device that has a very high Q and a small enough size to realize a comb. And more than that, these combs can actually be useful. And so this was really a kind of groundbreaking result, I would say, in terms of actually showing that these early combs could be used for something that could be like a clock. And this was work at NIST and Scott Diddams and Scott Papp's group. We simply provided a device here for them to do this. And what they showed is that one of the early forward mixing combs could be used to demonstrate a kind of simple clock based on optical frequency division of the D1 and D2 lines in rubidium. And here they're using not full self-reference in the comb. That didn't happen until much later, but actually two-point locking. So they're simply pinning 2 lines of the comb and then transferring the stability, the relative stability of the D1, D2 to the clock output in this case, which was at 33 gigahertz, and that actually worked. Okay, but now let's come to the more present time. There were a lot of issues with these early combs. I think those of us that were studying them at the time sensed that there was something missing. And it's shown here that the output waveforms were difficult to repeat. They were extremely sensitive to the conditions, the excitation conditions. If the pump wavelength changed a little bit, the whole comb would completely change. The combs were prone to serious instabilities. You simply couldn't get them to lock. And when they locked, they did not produce a pulse waveform. They would produce a very kind of random-looking waveform. So there was a kind of phase locking, but it wasn't reproducible. And it became clear that what was going on is that this was not what we would consider normal mode locking. Mode locking, when I would say the kind of classic idea of mode locking, we're thinking of terms of a uniform phase across all the modes that's going to produce a pulse, just as was the case with the Thai sapphire. And that pulse is important because that pulse actually guarantees that we have a repeatable and a stable temporal waveform, and therefore a repeatable and stable spectral waveform as well. And the pulses are also obviously important for broadening, which is essential to actually self-reference the comb. So something was missing, and the key point that has actually changed, and it was a very big turning point in this whole field just a few years ago, is the introduction of Soliton mode locking. So let's talk about that for a moment. So first of all, the picture to keep in mind for Soliton mode locking. Let's go back to this little ridge resonator, and with the silicon nitride waveguide, suppose we couple light in again. So we'll fill the resonator with photons, have this nice resonant buildup. But now something new is done. The resonator is going to be engineered, and we'll get into the engineering of this in just a moment. But the shape of the resonator is going to be precisely controlled using microlithography, microfabrication techniques, so that it will actually support soliton generation. And once this happens, it's possible to actually launch and actually trigger the formation of solitons. So here I'm showing one soliton. We can load the cavities with more solitons, but it's clear that what is now happening is that there's a periodic pulse train being emitted from the cavity, and this is a mode lock system, and so it actually produces a very, very stable and very nice frequency comb, but now in a chip-based format. So this uses the same effect. This is still using the Kerr effect, the intensity dependence of the refractive index, the third order nonlinearity, slightly different way. It's an ultra-fast process. And that's critical because the pulses that are being formed are going to be femtosecond timescale. They'll support a very, very broad comb. And in order for this to happen, the resonator, as I said, needs to be engineered, and we'll get into this. It needs to be what is now called dispersion engineered to actually allow the creation of these solitons. And then finally, as I said, this is a repetitive system. It's locking up all the modes in the traditional sense of mode locking, and it creates a very nice microcomb. So just as a little bit of background, and to be fair, optical solitons have been studied for a long, long time. There are actually there are really two flavors of them. There are spatial solitons, which were first introduced and studied in optics in the early 90s. And then the most closely related solitons to the ones that I'm describing today are the temporal solitons in optical fiber. And those were proposed theoretically in the 70s, studied intensely in the 80s. It was even considered at one point a viable way to send information over long distances. We don't do that, obviously, today. We use wavelength division multiplexing. But this interest in this subject has continued to the present day, and the physics, part of the physics of these solitons is exactly the same physics that's being leveraged in the microcombs today. So let's talk about that physics just a little bit. I want to dive in a little more deeply to show you what's happening and how the engineering works for these solitons. So the equation of motion is a nonlinear Schrödinger type equation. The part that I have circled in red is nearly identical to the equation of motion for solitons in optical fiber. And so there's a slowly varying field A. There's a dispersion term, second order dispersion term, which is that second term you see here. The phi is the coordinate, the angular coordinate of the soliton as it's orbiting around the cavity. And then there's the Kerr effect, the nonlinear dependence of the refractive index. That's proportional to the intensity, and this is a Kerr coefficient G. Now, as is true in the optical fiber solitons, the role of the Kerr effect is actually to compensate the second order dispersion. And so there's this balancing effect that goes on between these two terms, and this is common to both the microcavity solitons and the solitons in optical fiber. And kind of interestingly or curiously, if you wonder how the soliton is doing this, the soliton is actually trying to maintain its waveform. You can get an intuitive idea of how this works by actually relying on the name of the equation, okay, this sort of nonlinear Schrödinger type equation, and apply your quantum intuition, okay, to understand this process. So if we look at that not as an electric field equation, but think about it for a moment as a Schrödinger equation from first year quantum mechanics, replace A with psi, the second term d2 would be h bar squared over Tm. This would be the kinetic energy term of the particle in a box. And then here, the g magnitude a squared, that's going to be the potential well. But the potential well will now be proportional to the probability density, psi squared. And so you begin to realize that what the soliton does is the soliton writes its own well. So it is actually by, if it has the proper waveform, the proper amount of energy, pulse energy, it will actually create a potential well in the refractive index, and there is a self-consistent solution, the soliton solution, that actually will sustain itself. It actually performs this balancing act of dispersion with the Kerr effect. Now let's go on. Okay, so everything I've just said is common to these new solitons and the fiber solitons, but everything on the right is new. And the first important term, which does not appear in fiber solitons, is kappa. Kappa is the loss rate. So this is inversely proportional to the cavity Q, the optical Q. It includes things like scattering loss, absorption loss, waveguide coupling out of the resonator. But there is this loss term, and remarkably, these new solitons actually balance that loss. So the solitons are able to balance dispersion, but also balance the loss as well. And how do they do that? they use the parametric gain that we just talked about a few charts ago. So there's, as the soliton propagates around the cavity, it is actually able to regenerate itself. So this is not just soliton propagation, but this is a regenerative mode-locked parametric oscillator. It has this wonderful property of actually being able to sustain. On the far right, where is the power coming from for this process? It's coming from the pump. And the pump field that I illustrated in that little movie a few charts ago. And the pump is actually coherent, okay, with the soliton. So it's essentially a parametric process. The pump phase is transferred into the soliton. Even more than that, the pump frequency is part of the comb that will be formed. And so this means there is no need to actually lock a laser to the comb. The laser pump is already predetermined and pre-locked. Okay, it is indeed one of the comb teeth. One other thing I'll mention here is that actually there are these extra little terms I kind of glossed over. This is actually the cavity frequency that's being pumped, and this is the pump frequency. And because of the sign of G, this difference needs to be positive. And so all of the pumping that goes on in these cavities, the pump is slightly red detuned from the cavity mode. And we'll see a little bit more of that later. Little history. So this new type of soliton was actually anticipated theoretically many decades ago. There's an early paper in 1993 by Stefan Wabnitz that proposed this idea of this coherently driven soliton. It was many, many years later. It was 2010 until they were actually first observed, but the observation was not in microcavity. It was actually in fibers. And so fiber resonator work out of Stefan Cohn's group in New Zealand actually were the first to actually report and observe these solitons. Even more than that, they were watching what was happening in the field of microcombs at the time and made the connection, the important connection, that what they were seeing could be done in a microcavity. In fact, it would be important to try to transfer it to a microcavity. And so a few years after that, the first soliton microcombs were reported, beginning around 2014, first in crystalline devices, very shortly after in silica, and now if you come forward in time, many different platforms, silicon nitride, silicon, have all realized these little soliton microcombs. There's a lot of data that you can study in the literature. This is kind of representative, again, of what is out there, and I just want to show it to you to give you a picture of how stable and how nice these little soliton microcombs can be. This is, we're using a type of device here called a wedge resonator, and it actually has an external waveguide that's applied. But this is the spectrum, the optical spectrum that's produced as a result of the formation of the soliton and the regeneration. And you'll see there the pump line illustrated. That's one of the comb teeth. If we had a little bit higher resolution on that spectrum, it would be possible to resolve the actual lines themselves. They're about 22 gigahertz apart in this case, and that corresponds to the round trip rate. This is a 3 millimeter diameter cavity. And then you can also see painted in there a hyperbolic secant squared, that dashed red curve. And this is the spectral shape that is theoretically predicted from this nonlinear Schrödinger equation. And so you'll also note that this is a log scale, so that prediction is holding up over many orders of magnitude. And so it's giving you an idea that the modeling and the experimental work are in close connection. The modeling is actually very reflective of what we actually see in the lab. A couple of key points, and this is now sort of getting us in the direction, moving us in the direction of integration. The pumping power for these devices can be quite low. In the beginning, it wasn't. But as a result of some of the work going on with the systems programs, we're now able to generate solitons, and even at low rates, with power levels that are in the tens of milliwatts, as low as 10 milliwatts. And so this is a range where it's now possible to pump the soliton systems using 3.5 laser devices. So the idea of putting everything on a chip actually makes sense. There is other physics involved. I'll come back, I'll talk about the Raman effect in just a moment. But I want to note a very important thing is that the stability of the pulse train in these microcombs is exceedingly high. This is one way to show that. This is the electrical spectrum of a photodetected soliton pulse stream. You can see the rate, very high signal to noise. The phase noise of this, I have that if anyone's interested. But the phase noise is also quite low. It makes a very nice K-band oscillator all by itself. But the reason this is important is that we want to servo control these solitons. We want to servo control them as combs, and so the noise can't be too high. And so here the noise is very low, and so it's actually Very straightforward to servo control the combs for self-referencing. And now, the last point I want to make, which is a key point, is this idea of dispersion engineering that I mentioned earlier. The resonators that are used for microcomb generation did not support solitons originally. What was wrong? The problem has to do with this little term here. This is the second-order dispersion term. What happens if you look for this, what the dispersion is in a resonator that has not been properly fabricated, is something like this. This is a measurement. Let me explain it for a moment. This is a mode number or mode index, and this is a kind of a frequency scale. And each of those data points is a mode in the cavity. And we've measured that frequency, and we've made this plot by using a very carefully calibrated laser sweep. And we simply have scanned across the passive cavity, and we're looking at the cold cavity mode spectrum of a particular mode, particular set of modes. Painted in here is actually a parabola. This is kind of what we would like to see in order to have a dispersion that's reflective of second-order dispersion. But you see there are these wild deviations that are going on. And those deviations actually lead to higher-order terms. So you have derivatives and third derivatives, fifth derivatives that would all be very strongly influencing this nonlinear Schrödinger equation. In fact, it would actually no longer be able to support solitons. It's critical that that equation actually be dominated by this second-order dispersion term. We can have a little bit of higher-order dispersion. Indeed, that can be helpful, but it can't be pervasive over a wide range of modes. And so what's happening is interesting. This is actually the result of high Q microcavities being overmoded. They support many transverse modes. And if we imagine measuring the frequencies of these modes over some wide range, occasionally these modes will have accidental degeneracies. And when this happens, minute blemishes and imperfections in the cavity will actually cause those modes to couple. And so just as in any kind of system where you have something degenerate, you turn on a perturbation, there's a splitting. And in this case, it leads to this, what we call avoided mode crossing. So there's a big one here, there's another one here. These must be removed. It's essentially imperative that you remove these to actually generate solitons. Thankfully, this can be done. It took a little while to figure this out, but because there are wonderful numerical modeling tools now available that actually give us very accurate calculations of the complex mode spectra of these microcavities, because we have microfabrication tools that allow us to very precisely control the size and shape, the thicknesses of these devices, we can actually engineer them. You can design them, and in fact, it's now quite straightforward to do this. And this is representative of a device that's been optimized for soliton generation. You can now see the data follow along a parabola over a wide range. There's just a few little blips, and these are caused by some mode crossings that are coming through right here. And these are actually intensity profiles for the mode families, and so these are reflecting the cross-sectional shape of this resonator if we were to slice it. But here's the soliton-forming mode family, and here are these two higher-order mode families that are kind of blipping through and causing a little bit of trouble, but not enough to actually prevent the formation of solitons. And so this is what's done now across all of these different material platforms. So now, next step. Okay, so this is essential. This is the dispersion engineering, but I want to take this up a whole other level, which is essential for actually self-referencing the comb. So the first question is, where is the soliton in this picture? There is the soliton. What I've done is, this is not a measurement, but this is kind of painting in what the soliton that I showed in the previous chart would look like. I've even tried to give it a profile, an intensity profile. But you'll notice a couple of things. So these are the modes of this soliton that would form on this mode family. First of all, it's redshifted a little bit from the bottom of the parabola. And then the other striking thing about this is that it's a straight line. In fact, it's not even overlapping at all with the original cold cavity modes. The soliton has actually created its own dispersion, so to speak. And this makes sense. This is exactly what you would expect from this compensating effect of the Kerr effect against the second-order dispersion. So that is where the soliton's at. More than that, as we increase the power of the soliton will have some new interesting interactions with the material. There's an interaction that I want to show you right now called the Raman effect. And the soliton will actually begin to experience a change in its round trip rate as a result of interaction with the Raman effect. This will tilt this line. So the line will actually tilt a little bit. And then one other thing is that you can ask this kind of hypothetical question that we'll explore in detail here in the next chart, but there are these other mode families running around. What happens if a soliton actually bumps into a mode from another mode family? What's the effect of that? Well, the effect is that the soliton will actually begin to radiate. It will actually project its coherent power into another part of the spectrum, and a whole other family that is not even involved in the formation of the soliton. And you can actually see this. You can design this to happen. So here's an actual spectrum where we have a soliton I've kind of painted in. Here's a measured mode spectrum. Here's a crossing mode family, and here I've actually included all the data points for that mode family. It's very steep on this plot. The red curve, this is a linear scale now, not a log scale, but the red curve is actually the soliton spectrum for this particular line. You'll notice there's also a blue soliton there, and that blue soliton is what happens if I crank up the power just a little bit. When I crank up the power in the soliton, notice what happens to the curve. The line now tilts, but now it's tilting, and it's beginning to overlap with a mode, another mode family. And see what happens, or observe what happens now in the spectrum. There's now a little spectral blip, a spur. And this is actually now radiation that's not part of the soliton. The soliton is now just throwing coherent power into this mode. So this is an effect that actually has a parallel or an analog in optical fibers. It's called a dispersive wave. And you can engineer the resonators to generate many types of dispersive waves, not just that single mode dispersive wave, but here's a case where we've engineered a device to have a stronger avoided mode crossing. There's a shallower mode family over here. The soliton's bumping into it. And now what is observed is a collection, a family of modes that are actually receiving power from the soliton. So it's throwing its coherence now into another spectral region. Well, this idea is extremely important now for the modern self-reference microcombs. And here's why. This was a very dramatic demonstration reported just a few years ago where a silicon nitride resonator was designed to support a soliton. Here's the pump. But now you see this little peak. This is a dispersive wave, a collection of modes that are actually receiving this coherence from the soliton, but are now allowing, you can see the practical benefit of this, there's now power appearing at portions of the spectrum where the signal would otherwise be very weak. And this is almost 2/3, in fact, it's over 2/3 of an octave in this first report. Well, what has happened since the time of that is we've now learned how to not just engineer one dispersive wave, but create two dispersive waves. So there's a dispersive wave on the blue end, a dispersive wave on the red end, and this allows actually the formation of a full octave, even exceeding an octave, for purposes of self-referencing. And so we'll see how that works in just a moment. So now this leads to the final part of the talk, where we're going to now look at these chip-based demonstrations. As I said earlier, I'm going to focus primarily on the synthesizer, but the details of the synthesizer are very similar to the clock. And so let's look at that for a moment here. So the synthesizer belongs to it's a team effort, and it's been running now for 4 years. It's actually in the phase 3 of the DODOS program at DARPA. It just transitioned into phase 3. You can see the team members below that are all contributing different skills and different things. This is a diagram from our proposal 4 years ago, and the amazing thing about it is it's not too far off from what was actually demonstrated recently. And so let's just talk about it a moment. First of all, this is a synthesizer, so there's going to be a radio frequency input. It's coming here. This will give the system its stability. There's a comb down here, a self-reference comb. There's a very nice tunable high coherence laser up here, a 3.5 laser, that's going to be phase locked. There'll be phase lock control, phase lock loop control, and it will actually be able to synthesize these frequencies very precisely once the self-reference comb is running. Now I said self-reference comb, but you probably have already noticed that there's 2 combs there. There's 2 microcombs. So you say, why 2 combs instead of 1 comb? Well, this is a little peculiarity. I don't have time to talk about this. Some interesting soliton physics. If there's time, or if you're interested, I can talk about this after the meeting or after the presentation. But in terms of actually reducing power consumption, it turns out to be very advantageous to make the step from the radio frequency to the optical frequency in 2 steps instead of 1 step. And so what we do is we go from the radio frequency source to microwaves using what we call a fine-tooth comb. That comb in this case is silica. We need a very, very high Q there for that. That's why that's silica. And then the final step from microwave to the optical is actually done with a terahertz comb. So we can't, you could do it, but it would cost a huge amount of power to make that in one jump. And so we do it in 2 jumps, and that allows this whole system to run at very, very low power levels. So as I said, these combs can now run at tens of milliwatts. These run in the level of 40 to 50 milliwatts for a full octave. Okay, so this is just a trade-off that we make, a little bit of increase in complexity to lower the power. Now, how does this comb work when you have 2 combs? Well, the microwave comb here, the fine-tooth comb, is actually stabilized with the radio frequency source, and that's what's shown here. The terahertz comb does the hard work of actually self-referencing, so we get the offset frequency there. That involves some very tricky design of those double dispersive waves we'll see in just a moment. And then the silica comb then performs metrology on the line spacing of the terahertz comb so that we can actually lock down and phase lock the terahertz comb and reference it back all the way to the original radio frequency source. And then in the end, the tunable laser uses the grid provided by the microwave comb, the silica comb, to actually get its phase lock and actually tune very precisely across, in this case, the C-band, okay, the telecom C-band. So that's kind of how that works. This is a little more detail, a more recent schematic. This work was demonstrated in a sort of individual chip base platform, okay, where we had all the little chips, the 3-5 chips, the silica chips, the silicon nitride chips, all operating separately and then connected together with fiber optics. And this kind of shows you that chip configuration. Down here in the lower right shows the whole picture. Here is the double dispersive wave silicon nitride comb. You can see one wave there, one wave there. Here is the silica comb. So it's kind of hugging there, right in the middle. The silica and the silicon nitride share the same pump. So one of their comb teeth, okay, are actually phase locked or phase synchronized. Here's a zoom in of the silica. So we're now kind of moving in at this little range right here, or this little region. And you can see the silica. And this is the tunable laser that's actually now has the closed phase lock loop control and to extract the stability from the silica. And so this was, as I said, demonstrated and reported recently. And now, as I also mentioned, we're in the phase 3 of this program. Phase 3 is now going to eliminate the fiber connection between the chips, put everything into a very compact package. This involves some additional, I'd say just technical hard work to reduce the interface losses, pull the comb powers down just a little bit. They're already very low. And at the end of the day, this is actually there's a packaging engineer that's already starting to put the details together on this. This is what the final product will look like, and you kind of get the idea of the size. Here is, by the way, the silica comb. You can see how large it is in this case. So these are some measurements that are also available online in the paper. All of these measurements were done in the labs of Scott Diddams and Scott Papp at NIST. And this is probably one of the most important measurements I'll show right here, where the synthesizer, the chip synthesizer, is actually being compared with a reference synthesizer, which is a full erbium fiber comb. And so you've got the erbium fiber comb, and you've got the little chip synthesizer over here, and both of them will be driven by a maser. So they have a common reference, and you can already see what's going to be done here. We're going to just compare the frequencies that are predicted and the stability from the 2 sets of synthesizers. And so the first thing to do is, first of all, what is done? Well, what they did is they actually, they picked 7 or 8 lines extending over the whole C-band, some at the very extreme end, some more interior, beat the lines of the chip synthesizer against the tabletop synthesizer. That gives you a set of reference frequencies, radio frequency level frequencies that you can study. One thing that was studied was to look at the Allen deviation, and that is here normalized to 190 terahertz. That's the frequency of the optical frequencies being generated approximately. Actually, all of them are averaging down like this, and they in fact overlap with each other very nicely. And so what this is showing is that there's coherence, okay, between the tabletop and the chip-based synthesizer. And so this is what we would expect since they're being driven by this common radio frequency source. And then one additional measurement, there are others in the paper, but one additional key measurement is now calculate the frequencies for the output on the chip-based synthesizer two ways. First of all, take the frequencies that would be calculated from the chip-based synthesizer itself, but then also calculate those frequencies using the tabletop synthesizer with the benefit of now these beat frequencies between the individual comb teeth. So you run that calculation two ways, and that gives you an error in terms of what your chip-based device is, what the error is, or the difference between the chip-based device and the tabletop device. And this is what you see here for these different lines that are measured. And you'll see the errors are very low. In fact, most of the time, they're actually staying close to a hertz. So essentially, this shows that the microcombs are really doing their job. They're operating at the same level as this tabletop device. One other little measurement I'll show here real quickly is that this shows how well the phase lock control of the tunable laser works. And so this is a 3.5 narrow line width tunable laser. This was from the Bowers group at Santa Barbara. And here what is being done is the output frequency of that laser is being again measured by the tabletop comb, the tabletop synthesizer. And it's then being compared against what would be predicted from the chip-based synthesizer. Here there's a whole series of little steps that are being generated just to show this fine-tuning control. There's a beautiful movie that's on the NIST website. I think it's also on the DARPA website. But this is showing dynamic generation of frequencies just to show you the level of control that's possible with this kind of device. And then real quickly, before I run out of time, this is the reverse. So this is another program, the ACES program team is shown below. And a lot of overlap between the two teams, but there are some new team members. And here we're also using a dual comb approach to reduce power consumption. We're going from the optical down to the electrical. And the key point here is that the optical synthesis or the optical reference is this two-photon rubidium transition that Zachary Newman talked about yesterday in his talk. And so I would just refer you to that talk, which did just an excellent job of going through the details of this for more information. And I think there's a paper in review or in preparation here that should also be available perhaps on archive fairly soon. Before I close, I just want to note that this whole idea of putting microcombs on a chip would be impossible were it not for the availability and ongoing work that involves the heterogeneous integration of 3.5s, lasers, modulators, photodetectors, with silicon photonics. And this is an area that really has been pioneered by the Bowers group at UCSB. And he has played a very prominent role. He's led, the DODOS effort, the synthesizer effort. Apart from the available technology, there's also new technology that needs to be invented. It has been invented as part of the DODOS program. And one is the ability to flip chip die bond F2F, these nonlinear doubling crystals, into a wave-guided format so that they can be integrated. And there's two different material systems that are being studied heavily there. One is the lithium niobate system, which is kind of the workhorse for frequency comb technology. The other new one is gallium arsenide, which is looking very, very promising. And then in the lower right, I'm showing that there's ongoing work on isolators. This is still a kind of a nagging concern. I think the industry needs a wave-guided isolator. There's been progress in that area, but there's more work that's necessary. And then a last little note, I spent a considerable amount of time talking about these dispersive waves as a way to broaden a comb out to an octave. The way, as I mentioned earlier, that it's done in conventional combs uses, for example, this kind of technology, nonlinear optical fiber. I'll point out that there is potentially another way to do this on a chip, and this is to essentially move the fiber to the chip. And there's actually an array of little silica waveguides here. This is a zoom in of those arrays, or that array. There are TISAF pulses being launched on the left, and each of the waveguides in this array has been designed to have a slightly different dispersion so that there's a phase matching point at a different wavelength into a dispersive wave. And you can see that these beautiful colors from the visible all the way down into the deep UV are efficiently generated using this kind of technique. And so this is a beautiful way to actually replace nonlinear optical fiber. It's a really powerful technique. You've got more materials to look at besides silica. There's the chalcogenides, there's silicon, silicon nitride. And even better than that, there's many devices that can be put in parallel on a chip, and you can vary their properties so that in the lab, it's possible to sort of fine-tune where you would like to be. And in fact, this is kind of an ongoing area that's being studied by a number of groups. So now I'm going to close, and I want a series of acknowledgments. First of all, obviously, acknowledge DARPA and the great leadership at DARPA that had the foresight to drive these synthesizer and clock programs. I want to thank our sponsors at CalTech. I want to thank also a lot of my colleagues who contributed many of the charts that I used today in this talk, the Dodo synthesizer team, the ACES clock team, my own students at CalTech. And then in terms of where this field is going, I don't have to say too much about it. I think it's very clear microcomb technology is moving very, very rapidly in terms of its performance. The power is dropping. The bandwidth is where it needs to be. If there was one thing we'd like to do is we'd like to get rid of the need to use two combs. Okay, if we could use one comb, that would be better. But right now, the two-comb technique is working fine. The 3.5 technology, the silicon photonic technology, is advancing in parallel. It's there and ready to use. And there will be, very soon, prototype integrated comb systems that are going to be multi-cubic centimeter in size. How long it will take for those prototype systems to become field deployable, that's an open question. That will take many years because there needs to be some effort put in to identify applications that can support some of the additional NRE involved in doing that. There's a lot of other applications. Obviously, I didn't have time to talk about today. There's a lot of interesting science going on just having to do with these new solitons, these parametrically amplified solitons, formation of new solitons, formation of soliton states involving multiple solitons, and then applications for these small devices. Someday there will be little butterfly packaged combs, fully self-referenced combs. And those would be obviously great to put into space, perhaps clocks in space that are optical clocks. Chip-based buffers, this was one of the original ideas for this parametrically amplified comb. I think it's ripe again for consideration. And then one that I have no idea about, but I throw it out there because I still think it's fun to speculate, is that it is now easy to put N combs on a chip. And what could we do if we can put N combs on a chip? Are there new things that will happen as a result of that? And I really don't, as I said, I really don't have an idea, but it's fun to think about this. And so that's where I'll stop. And I want to thank all of you for your attention. And this was a lot of fun, to talk about today. Okay, thank you.
Are there any questions?
What methods are used to engineer the spurious modes in your little resonator? Mm-hmm. Get them away.
Yeah. Okay. Yeah. So let me go. So thanks for asking that question because it gives me a little bit more time to explain actually what we do. So this would have been very difficult to do, I think, probably 15 years ago. But probably many of you, I'm sure, benefit from the powerful simulation tool called COMSOL. And so we are big users of COMSOL. And what we do is we actually will take a geometry that we have. It could be a ridge, it could be a wedge. And we're not the only ones that do this. This is sort of a standard technique. We will very carefully measure it. We will introduce the Sellmeier equation, to actually profile the refractive index dispersion, the chromatic dispersion. And then we will simulate it. And so this simulation will then provide us an entire mode map. And that mode map, we then look into it, and we can see where we are, where there are mode crossings, and we can begin to play games with the actual geometry itself. And so by doing that in the largest structures, you can find clearings, open spaces where it's possible to form a soliton. We have designs for this now in our large wedge resonator that run at 1.8 gigahertz, at 4 gigahertz, at 9 gigahertz, at 10, at 15, at 22, at 30. And it's all been this process of iterative design. Once you have the design, you simply reproduce it. And the reproduction involves simply being careful in microfabrication. So it's using a stepper tool to actually do your lithography. It's being careful about the temperature of your etch baths and calibrating your etches. It's doing all of that right to actually produce a reproducible geometry. And if you do all of that right, you have tremendous yield. You can crank out these devices. So it's a recipe-driven kind of design. Some of the newer devices that are coming out actually have fewer mode families. And so the tendency for avoided crossings is reduced. those are dramatically easier to design. And so the ridge geometry structure that I threw up that we've developed for dodos, there we can actually find clearings, okay, very easily in the spectra. Yeah.
Thank you.
Mm-hmm. Yeah.
And that's really about the integration aspects of your work. So I'm curious about whether, so you now have, if we want to make a comb system that can be in a butterfly package, the pieces all have to be put together. And I'm curious about whether you think that that has been a problem that's been largely solved within the photonics community, or whether you will have to really do some new research in terms of being able to integrate those things together reliably and efficiently.
Yeah, that's another great question, and I think so. It's a one we're obviously bumping up against right now in both the synthesizer project and ultimately in the clock project. And my own answer to that question is sort of guided by what happened in telecommunications. And so in telecommunications, your immediate thought, and this goes back about 20 years ago, your immediate thought is that integration is great, and we need to put everything together on one chip. And the actual answer is that probably in the beginning, it's better to actually have separate functionalities isolated on different chips. You want a certain level of integration that's going to support actually, the economy of scale that's possible with microfabrication. But there are very costly things that can happen that will drive down the yield of the overall process. And those can be addressed by simply having separate chips and doing free space coupling. And despite the fact that free space coupling sounds very expensive, for many years, and I think it even continues to this day, free space coupling, even on fairly complicated transceiver packages, what are called diplexers and triplexers, which are used in fiber to the home applications, those are done with free space optics. And they're just now beginning to transfer over to fully integrated designs, but that's being driven by data centers. And so, like I say, it takes a certain level of investment to actually solve all of the problems simultaneously. So my answer is that I think for some time, the design of these little tiny chip systems will involve perhaps 4 or 5 separate chips, each of them with an important subsystem on board, but then some kind of clever free space coupling in between. Very similar to the dodos and also the clock design. Yeah.
We have time for one more question.
I just wanted to ask a question. Thanks a lot, first of all. It was a great talk. I think for the Soliton generation, the main nonlinearity that you use is the Kerr effect. I think you touched upon it in one of your slides, but I was wondering, what's the main benefit of using the non-centrosymmetric materials? Presumably other nonlinearities like second harmonic generation.
In other words, I could use a Chi2 essentially for. You're thinking.
So what
Are you thinking of just the silica system or any of the glasses, for example?
No, like the gas or the lithium niobate or the aluminum nitride.
Oh, I see. Why are we using those?
Yeah.
Why are we interested in using those? Yeah, those we need because of the Chi2. Okay, so we need a Chi2, and so it's essential for the frequency doubling, the F2F process. That's closing the loop on the short wavelength side, or the low frequency to the high frequency self-referencing process, F2F. We need a doubler, there. And so the materials, they need to support a Chi2. And so that's why we need these materials like lithium niobate. We can't do that. I say you can't do it. You can't do it with silica. There are ways to sort of break the symmetry by looking at the interfaces, and there's even some reports about this in the literature. But for the most part, you want to do it with a material that supports a Chi2, and that's why we need piplin, we need gallium arsenide, we need these other materials, right? Yeah.
Okay, very good. So